All right, here's the third in our series of online videos. Today we're going to be finishing up Chapter 10. We're going to be looking at whether something is considered polar or nonpolar. So you might want to go ahead and print up the notes for this. They're on the website, and on the website the notes are called polar or nonpolar, and then it'll say practice. So you might want to print those up before you start watching this video. Now, this whole topic is a very important one in chemistry. It helps determine how a compound behaves, whether or not it's polar. From the textbook here on page 341, they give you a simple picture of oil and water. And everybody knows that oil and water, they don't mix. Well, the reason they don't mix is water is a very, very polar substance. Oil is nonpolar. And generally speaking, polar things don't mix with nonpolar things. This will become really important in Chapter 12 when we start talking about intermolecular forces. Now, a little bit of review is in order. And the pictures on the printed notes I took right from the textbook here. They look a little better in the textbook, so I'll stick with this. When you have a covalent bond, say you have a covalent bond between this oxygen and this hydrogen. Well, because oxygen is more electronegative, oxygen is going to pull electrons towards it. Remember, you have two electrons that are being shared here. Oxygen has a higher electronegativity, has a greater ability to pull those bonding electrons over that way. So if you look at the electron cloud, that's what they're trying to show with all these little red dots, the electron cloud. You can see how the electron cloud's pulled over to the left there towards the oxygen. Because of that, this end of the bond becomes a little bit negative. The other end of the bond becomes a little bit positive. You'd say that is a polar bond, and they call it a dipole moment here. Now, sometimes dipole moments are shown with symbols like this. You have a little arrow pointing towards the more negative end of the dipole. The little tail with the built-in plus sign is over here towards the more positive end. Again, the little squiggly means partial. So this is saying partially positive, partially negative. Electronegativity bears a little review. I gave you this picture in my notes. That's right from the book listing different electronegativities. I'll be honest, all you really have to know here about electronegativity is that electronegativity increases as you go up a group, and it increases as you go over. And the big thing to know, the three most electronegative elements. The most electronegative element is fluorine. The second most electronegative, oxygen. The third most electronegative, nitrogen. So know that these three are your heavy hitters when it comes to electronegativity. That's going to be huge later on. You don't have to know the actual values of electronegativity, just know the trends. Okay, now they show you a picture in the book kind of similar to what I have in my notes here. In fact, in my notes it's a photocopy from the book, and it's showing when you have a bond where both elements are the same, both these elements are the same, the electron cloud is nice and evenly distributed, and you'd say that is a purely covalent bond, 100% covalent. If you have a bond where the electronegativities between this element and this element, the difference is, in this area, 1.5 or so, it's getting to be a kind of a polar bond. And if the electronegativity ends up being 3.5, more than 3.5, then the bond essentially breaks and you have an ionic bond. So you'll find a picture like that in the textbook, and there it is. So it's just showing you that as the difference in electronegativity between the two atoms changes. If there's no difference in electronegativity, perfectly equal sharing of the two electrons. In this picture, hey, this element is more electronegative than this element. So the electrons are pulled over this way, and that's a polar bond. When the electronegativity becomes really large, around 3 or so, the bond essentially breaks, and you have a positive ion and a negative ion. Then you have an ionic compound. So it's a whole range on electronegativities there, or on polarity. Now, what you want to be able to get out of this section is we're going to give you formulas of compounds, and based on the formulas, you're going to have to draw a Lewis structure. Based on the Lewis structure, you'll have to predict the shape. Then you'll have to say, is the compound polar or is it nonpolar? And again, that largely determines how the substance behaves. Polar stuff tends to dissolve in water. Nonpolar stuff tends to dissolve in oil. Oil is nonpolar. I'm sure you've heard of vitamins being either water-soluble or fat-soluble. Water-soluble vitamins, they dissolve in water. You can eat lots of those vitamins. Your body will just flush them out. Fat-soluble vitamins, those are things like vitamin A. You don't want to overdo it with those because they'll dissolve into your fat. They're not flushed out periodically, and you can actually build up a pretty high level of them and kind of overdose. So fat-soluble vitamins, you have to be careful with the dosages. So again, solubility is largely based on that polarity thing. Okay, so if you want to determine if something's polar or not, you always have to start with the Lewis structure. So here's our first example, nitrogen trifluoride, NF3. Say you're taking a test in a couple of weeks. Don't know how we're going to do the testing yet, but I'll let you know as soon as I figure it out. You're taking a test and you're asked, is nitrogen trifluoride polar or nonpolar? What do? First thing you do is draw the Lewis structure. For this particular compound, your Lewis structure will be this. Now I did that very quickly, but that's because I've been doing this forever. You might have to review those rules for drawing Lewis structures. So that's your Lewis structure for NF3. Second thing you have to do, you have to apply Vesper theory and figure out what's the shape of this guy. Is the shape of it going to be kind of like this? It's got three things bonded to it, right? Or is the shape of it going to be more like this, where it's more three-dimensional? If you remember the video on Vesper theory, how do you determine this? Oh, you do your Vesper count. You do your steric number. How many things surround this central atom? 1, 2, 3, 4. So if I go to build this, I have to build it using one of these things with 4 different prongs, one of these tetrahedral arrangements of atoms, and that would be this one. And if in this particular model, we'll pretend that this is the nitrogen. These are my 3 fluorines, and that right there is that little nub there is my dot dot. That's my lone pair. So again, you're seeing an application of Vesper theory here. You have 4 things around the central atom. That's the shape this thing would take on. So even though you might draw it and it might look flat, it's not flat. It's quite three-dimensional. Now, individual bonds here. This bond between the nitrogen and the fluorine, is it polar? That's the easiest question in the world to answer. If it's two different elements, they have two different electronegativities. Nitrogen, fluorine, they have different electronegativities. You know that fluorine is the most electronegative, so this guy is better at pulling the electrons over, so the electron density is going to get pulled this way. So yeah, that bond is polar. This bond is polar. This bond is polar. And based on the shape of it, this one's shaped like a three-sided pyramid. It's showing you, hey, if you have a dipole here, here, and here, the overall effect is that the electrons, if the electrons are being pulled by those three fluorines, the three yellow atoms, the net effect is pulling the electrons this way. So yes, this is a polar molecule. So you would say NF3 is polar. Now, it can be tricky. Check it out. What if it had this shape? What if you had something that was flat like this? If, indeed, that was the correct shape. It's not. NF3 is not flat. But if it were flat, like this, and you had electrons being pulled this way by this fluorine atom, that's my dipole, that little arrow. You had electrons being pulled this direction by this atom, and you had electrons being pulled in this direction by this atom. The overall effect of those three forces pulling on the electrons, they all cancel out. And then you'd say the molecule is nonpolar. And you're seeing that over here. You'll see this diagram in your book as well. If it's flat and three things pull in equal directions, it is nonpolar. So you could have a nonpolar molecule with polar bonds. So the bond is polar. Is the molecule polar? No, not if it's flat like this. The way to think of this, the easiest way to think about it, when you're trying to determine polar or nonpolar for the molecule, pretend that the central atom is a boat floating in a lake. So this boat's floating on the surface of a lake. And you have this real strong guy with a rope attached to the shore, and this guy here is trying to pull the boat this way. This guy's trying to pull the boat this way. He's got a twin brother, actually triplets. They're triplets. They're all pulling equally hard in these different directions. You have to ask yourself, if they pull equally hard, will the boat move? In this case, no. Those three forces, the forces of these guys trying to pull the boat to shore, will all cancel out. It's a little bit more obvious if you look at a linear system, say like this. Again, pretend this is your boat floating in the lake. And one guy's trying to pull the boat this way, the other guy's trying to pull it this way, and they're both pulling equally hard. Equally hard. Does the boat move? Nope. The two forces cancel each other out. And you would say the molecule is not polar. Even though you might have a polar bond, another polar bond, but if they're pointed in opposite directions, those two forces can cancel out. Same thing for this flat one. Now, if it's not flat, however, if it's, as we showed you here for the NF3, if we had this, again, use that analogy of the boat floating in the river or the lake. Pretend this is my boat floating on the surface of the lake. There's somebody below trying to pull the boat down, somebody below over here trying to pull it this way, somebody else tries to pull it this way. What's the overall effect? The overall effect is to pull the boat down, right? So you just ask yourself, will the boat move? If you answer yes, that molecule is polar. Let's do some more examples here. So for carbon dioxide, and I'm just going to give you the Lewis structures real quick. And the step-by-step stuff here is, of course, if you're asked polar or nonpolar, first you have to get the right Lewis structure. Then you have to correctly apply Vesper theory. Then to figure out if it's polar or polar, you ask, will the boat move? So carbon dioxide has this Lewis structure. So that's the Lewis structure. According to Vesper theory, it is linear. So if you were to build it, you would end up with this. You have a dipole going here. I'm not going to try and show the double bonds in my model. That's too hard to do. So you have a dipole pulling that way. You have a dipole pulling that way. 180 degrees. So one guy's pulling this way, the other guy's pulling equally hard in the opposite direction. They're pulling equally hard in opposite directions. Does the central atom move? If you answer no, you'd say it is a nonpolar molecule. So this is a nonpolar molecule with polar bonds. So the individual bonds are polar. The molecule as a whole, not polar. So if I ask you, carbon dioxide, is carbon dioxide going to be more soluble in oil? Or is it going to be more soluble in water? Oh, oil. Yeah, because it's nonpolar. It's going to like a nice nonpolar solvent. And you see it when it's in water. When you do have it dissolved in water, it wants to come out of the water. It bubbles out. That's how you get fizzy water or carbonated beverages. So, not a polar molecule, but it does have polar bonds. Polarity can be measured, by the way. We have instruments that can determine just how polar a substance is. It's a real thing. It can be measured. Okay, how about sulfur dioxide here? If you draw the Lewis structure of sulfur dioxide, you'd come up with something that looks like this. Sulfur in the middle, double bond, couple of lone pairs, single bond, you'd have 3 lone pairs, and you'd have a nice dot there. That's the correct Lewis structure for SO2. So that's my Lewis. If I apply Vesper to this, how many electron groups? 1, 2, 3 electron groups. So if I go to build it, I'm going to come up with a bent shape. So according to Vesper, this guy is bent. So there's my molecule. Again, this is supposed to be the sulfur in the middle. Forgive the color code. We usually use yellow for sulfur. I ran out of yellow atoms. So there's my sulfur. There's my oxygen. Hey, is the bond polar? Real simple. 2 different elements, the bond's almost certainly going to be polar. You know, oxygen's one of the 3 most electronegative elements. See, we'll have a dipole there. That bond is a polar bond. This bond likewise is polar. It's equally polar. So you have this boat floating in a lake. You have a guy on shore trying to pull it this way. You have a guy on the other shore pulling this way. Will the boat move? Yes. I always get people that say no, it won't move, that these will cancel. No, if he pulls this way and he pulls this way, let's do it with my pens. If they both pull equally hard, the boat will move. It'll move that way. So yeah, you would say that the overall dipole is going, there's an overall dipole, they'll sometimes say net dipole that way. Because if he pulls this way, he pulls equally hard this way, that boat's going to move in that direction. So this is a polar molecule. This is a polar molecule. Which one would you expect the sulfur dioxide to be more soluble in? Oil or water? Oh, polar things like to dissolve in other polar things. It's more likely to dissolve in the water than the oil. Okay, so those are our first two examples. Let's see, we have three more quick ones to do. We have sulfur trioxide. So we have SO3, and the Lewis structure for that guy is sulfur connected to the three oxygens. There's your sulfur trioxide. If you apply VSEPR to this, valence shell electron pair repulsion theory, the VSEPR shape that you come up with will be trigonal planar. That guy's nice and flat, right? You'd have the 3 count here, so 3 things. You have to build it based on this. Let's pretend that my blue is the sulfur and my reds are the oxygens. You have this nice flat system, perfectly flat, symmetrical. So you have a dipole going this way, you have a dipole going that way, and you have one going that way. That's a pretty bad looking arrow there, but you have the 3 dipoles. That's supposed to be an arrow. Sorry. So if these 3 guys pull in these directions and they all pull equally hard, will the boat move? No. Those 3 forces will cancel each other out, and that central atom's not moving. So you would say this is a non-polar molecule. Non-polar molecule. Yes, he has polar bonds. The individual bonds are polar. But the effect of those 3 bonds pulling simultaneously is to cancel out any forces. So it's a non-polar molecule. 2 more quick examples. This one's pretty easy, the CF4. The Lewis structure for the CF4, carbon tetrafluoride, would be this one here. According to VSEPR, the VSEPR shape is tetrahedral. So I have to build it based on that thing with 4 little connectors. I'm going to pretend that the fluorines are the yellow atoms here. So here I've got my CF4 molecule, and black is the carbon atom in the middle. The yellows are the fluorine atoms. And I haven't really explained to you guys how to draw a tetrahedral. Some people can draw beautifully in perspective. Most people can't. So if you ever have to analyze these shapes, it helps to have a system for drawing the tetrahedral shape. Here's the way it's done. You pretend that you have your central atom and you make a little check mark there. And for anything in your drawing where you have a simple line, you assume that this atom, this atom, this atom, they're all coplanar. They're all sitting on the same plane, the same flat surface. But of course, you also have something coming out towards you. Now, guys, most of us can't draw very well in perspective, so chemists have developed a little shorthand here. If something's coming off the plane of the page towards you, we draw that bond with a wedge here. So what you're supposed to see here with this little F, that little wedge means it's coming towards you. So that little wedge, that wedge means it's coming off the plane of the page towards you. Now you have still one more fluorine atom, and you can see how that one's going back behind the plane. The first three atoms here are the plane. You have one coming up and one coming down. The little shorthand notation we have for something going away from you is to use a kind of a dash, dash, dash. So you'll see this notation. This will serve you well if you take more chemistry when you're looking at complicated structures. If they have a little wedge, it means it's coming towards you. If they have a dash, 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 it means it's fading away from you, away from the plane of the page. So anyway, you learned a little bit of notation that you'll see with more structural chemistry there. So if you look at this one, it's quite symmetrical. So if this is your boat in the middle, and this guy's pulling this way, this guy's pulling this way, somebody's pulling this way, and somebody's pulling straight up, those four forces, because it's so symmetrical, those four forces will cancel, and you would say this is non-polar. So this is a non-polar molecule. Last one on here is the tricky one. On the third test, I usually have a question that has one similar to this. It's a little tricky, and yeah, it's usually the most missed problem on the test. So, dihydrogen difluoromethane here. The Lewis structure is going to be this. You have fluorine bonded to carbon, bonded to fluorine, bonded to hydrogen, bonded to hydrogen. So that's your Lewis structure. Now, the reason this is the most missed problem on any test is people look at this and they say, oh yeah, I got this down. If I have a dipole here, remember fluorine's the most electronegative, so people think I have a dipole pulling this way, I have a dipole pulling this way, those two dipoles will cancel and they'll say it's nonpolar. Wrong. This is definitely a polar molecule. This is a polar molecule. Now, why is it polar? Oh, what did we forget to do? Apply VSEPR theory. If you look at the VSEPR shape here, the valence shell electron pair repulsion shape, it's tetrahedral. It's not flat. The Lewis structure is drawn on a flat surface, so it's easy to draw the Lewis structure and make it look like these two things will cancel. but it's not flat. It's tetrahedral. So, if we build that thing, it's going to look more like this. There's my tetrahedral shape. So you have a hydrogen atom here, you have a hydrogen atom here. The difference in electronegativity between the carbon and the hydrogen is really small. Turns out the carbon's actually more electronegative, so rather than this pulling, it's more like the hydrogen's pushing, but it's a real small effect. Now, the big effect is, oh, this fluorine's pulling this way, this fluorine pulls this way. The overall effect is to pull that way. So if you had to draw it, you could draw it like this. You could say carbon bonded to fluorine, bonded to fluorine. You put your hydrogens here. Again, the hydrogens are having very little effect on it, but that's your tetrahedral drawing. And you'd say, hey, I've got a dipole, a pretty good strong dipole from the fluorine pulling like that. I got a good strong dipole from the fluorine pulling like that. The overall effect of these two things pulling is to pull the thing that way. So you'd say it is a polar molecule. And for what it's worth, each of these hydrogens will have a little push. They'll actually have a small dipole going towards the carbon. So anyway, that's polar versus nonpolar. Conceptually, it's not too tough. I gotta be honest with you, people have trouble with it because you have to do three things here. First, you have to draw a Lewis structure. Second, you have to correctly apply Vespr theory. And then you have to visualize the thing. And then it's kind of easy to make the determination of if you're polar or nonpolar. If you don't do this Vespr shape, ooh, that's where you end up making mistakes. So, anyway, hope you enjoyed the video. Next one coming soon.